bent on capturing an image of the impossible now on BBC4, on a mission to unlock the universe's greatest mystery, to see a black hole.
The universe holds a giant cosmic secret. Nobody's ever seen what a black hole really looks like. Now a team of international astronomers are on a mission to find out.
There we go. We're on.
The team's director has dedicated his life to take the first ever picture of a black hole.
If you ask why this hasn't been done before, it's because it's really, really hard.
For 2 years, our cameras have followed these scientists to the most hostile environments in the world.
It's pretty cold. The wind chill right now is around -70.
As they build a revolutionary telescope the size of planet Earth. If they succeed, a picture of a black hole will challenge the theories of Albert Einstein and could pave the way to a new era of physics.
It will be one of the most thrilling discoveries of our age.
This is the inside story of the mission to capture the first real picture of a black hole. Of all the wonders in our cosmos, one object has remained hidden to the greatest scientific minds. The black hole.
A black hole is a region of space where the pull of gravity is so powerful that nothing at all can escape if it gets too close. And by nothing, I really mean nothing, including even light itself.
What we really mean by that is this area called the event horizon. It's a specific limit around the black hole that marks what's inside and what's outside.
Once anything crosses that boundary, adios. It is out of contact with the rest of the universe. We don't know what its ultimate fate is, but probably it ain't very good.
Most scientists today believe that black holes really exist. But nobody has ever actually seen one.
We have identified lots of objects that look like black holes, but you can't prove that they're black holes. This is where the problem comes, right?
If nobody has ever seen a black hole, can we be sure that they really exist? Could this fundamental notion about our universe and how it works be wrong? Astronomer Shep Dolman is on a mission to solve this mystery. He's spearheading an extraordinary experiment. He wants to take the first ever picture of a black hole.
The goal of the entire project is to see what a black hole really looks like, and detect its shape, and see what's happening immediately surrounding it. I mean, just saying that gives me chills. I've been interested in black holes since I began doing astronomy. It's really kind of what got me into it in the first place. I kind of fell in with this crowd doing radio astronomy in a very special way.
Here at the Haystack Observatory and across the world, Shep has been developing a technique to try and see the unseen. Shep is targeting the very center of the galaxy, where astronomers have detected a cluster of stars orbiting something strange. The stars are orbiting so fast, scientists have calculated the object must have the mass of more than 4 million suns. The best explanation, a black hole called Sagittarius A star. Shep wants to use radio telescopes to try and see this black hole. But there's a problem. Although it's predicted to be larger than the sun, from Earth, is 26,000 light years away. This is such a small target. There's no telescope in existence that has the power to see it.
The entire reason this hasn't been done up till now is that black holes are extremely small. It would be the equivalent of trying to see an orange at the distance of the moon. So we have to build a telescope. We have to build a fundamentally new instrument that can see things that are that small.
To achieve this unprecedented power, for the last decade, Shep has been working towards a master plan. He wants to combine 8 separate telescopes in Spain, Mexico, Arizona, Hawaii, Chile, and the South Pole. This network is called the Event Horizon Telescope and spans the face of planet Earth. To capture the crucial image, all 8 dishes must point towards the black hole at exactly the same time.
We're linking telescopes about 10,000 kilometers apart, even more than that. By spanning the globe, you create a new kind of instrument that can see a black hole. That's the secret sauce. That's the secret of the Event Horizon Telescope.
Each of the 8 telescopes in the network are unique and powerful observatories. They can detect emissions from around the black hole, but the team will need to combine these signals to make an image. Across the world, the team will observe the black hole simultaneously and record the data onto hard drives. Then they must physically transport the drives back and combine the data inside a giant supercomputer called a correlator.
This correlator is the final piece of the puzzle. The first part is collecting data at different spots around the globe. The second piece, though, is combining that data, and that's what the correlator does.
Only then will this new Earth-sized telescope have a chance to make an image of a black hole.
If the Event Horizon Telescope manages to actually take a high-quality photo of a black hole, that's not an impressive feat. It's a mind-blowing feat. It's a technical tour de force like we've never seen before.
But what does Shep's team hope to see if a black hole allows nothing, not even light, to escape? A black hole itself is invisible, but matter falling into it should give it away. Its intense gravity attracts interstellar gas and pulls it into a faster and faster orbit. This heats the gas to billions of degrees and emits the light that the telescopes should be able to detect. The mathematics suggests gravity will warp these emissions into a circular ring, leaving in the center the shadow of the black hole. It's an important scientific prediction. If the team sees something that isn't circular, it could turn the most treasured theory in physics on its head. Einstein's theory of general relativity. His theory says mass curves the fabric of space and time, creating an effect that we call gravity.
Einstein's theory of relativistic gravity is what lays the foundations that sets all of our understanding. Step one is just, did Einstein get it right? Is there some detail that's been overlooked?
For 100 years, Einstein's theory has passed every test, but nobody has ever seen its most extreme prediction. If enough mass could be crushed into a single point, its gravity would be so strong it would form a black hole.
How wonderful would it be if the Event Horizon Telescope shows us that in extreme realms, Einstein is not completely right? It will be one of the most thrilling discoveries of our age, as we will then leapfrog forward in our grasp of how the universe works.
A challenge to Einstein's theory, and a new era of astronomy rests on the success of the Event Horizon Telescope team. There are now just 3 months until the team will attempt to observe a black hole using a network of 8 telescopes. But there's a lot to do. Shep has come to Mexico to oversee a crucial test run using 4 of the 8 telescopes in the network.
What really gets us out of bed, what really gets us motivated for this, is building a new kind of instrument. When you think of building a telescope as large as the Earth, that in and of itself is such a crazy idea.
To link the telescopes, the team will use a technique called Very Long Baseline Interferometry, or VLBI. But it poses a major challenge. During the observations, they won't see any results in real time.
The very nature of the technique we're using is that we're not going to know if these observations work until we get all the data back to a central processing facility. So we're here to do what's called a dry run, to make sure that everything runs like clockwork.
Scan 2. Oh, somebody at 0.78. It's 0.078. Who wrote that?
We have crack ninja teams here in Mexico, in Chile, the South Pole, Spain, and they all know their business, frankly. They know what to do. You check everything, and you check it again, and you check it 3 times.
During the critical observation run, there's a lot that can go wrong. The radio emission from the black hole must be recorded at each telescope, and the data stored onto specialized hard drives. But clouds can obscure the signal, and equipment could fail, knocking one or more of the telescopes out of the network. So the team need clear weather and perfectly working telescopes at every location across the globe simultaneously. If just one telescope fails, they might not get an image. After the data have been recorded, the filled hard drives will be shipped to Massachusetts and Germany, where the data must be combined, and they will know if their ambitious plan has worked.
You think it's all set?
Yeah, I hope so.
Okay.
In Mexico, astronomer Gopal Narayanan is in charge.
The whole purpose of the test observations we're doing is to bring in a couple of new facilities. We're going to bring in OPEX, which is in Chile, Pico di Valletta in Europe, and the South Pole Telescope.
The South Pole is a critical location for the team. Its clear, frozen skies are perfect for observation. But flights here will soon stop for the winter, which means the data from the South Pole will be the last to return. Instrument expert Dan Maroney and his team have traveled here to the ends of the Earth to get the telescope ready.
By including the South Pole Telescope, we really truly make a telescope the size of the Earth. It more than doubles the resolution of the array and gives us that last bit of detail that we need to make a picture of a black hole.
It's January, and the weather is a biting 36 degrees below zero.
So it's pretty cold. The wind chill right now is around -70.
Despite the cold, the team still need to prepare for the test observations. They must install this custom-built mirror to the telescope with sub-millimeter accuracy.
Okay, I do believe the tertiary is installed.
We have to have this mirror positioned so that the light from this giant 10-meter telescope is focused precisely on our receiver. So that took a little bit of doing, but we think we have it right about now.
The mirror is in, but until the observations are complete, they won't know if it's worked. Back in Mexico, Gopal and the team get ready to start the trial observation run with the 4 telescopes. They will observe bright sources called quasars to help test the new network. Data specialist Lindy Blackburn is in charge of recording the data.
1 minute to go.
1 minute to go. Is Lindy happy with this? There we go. We're on.
But as the test observations begin,
Okay, recording.
there's an unexpected problem.
Noise.
No lights?
A bug in the code means the recording lights are not coming on.
No, it's trying to record.
I was trying to record. Okay. Sending data to record, only the very last step in this whole fine process, which is, albeit a very important step, which is to record the damn data we've collected all through the chain. That is not happening right now.
Without data, the telescope is knocked out of the network.
Lindy is working furiously to find the fixes, and I think we're hopeful. So the IF levels look fine.
Yeah.
Tell me it's working, Lindy. No.
Same problem.
Yep.
I changed the order when I thought it was the initial problem with the...
You're hoping that we'll get this recording this time, Lindy?
I really don't know.
1 minute.
Already?
10 seconds to go.
Lights. Yay! Good job, Lindy.
It's 2:46 a.m. The team have succeeded in recording the test data. But they won't find out if it's worked until the data have been analyzed. Only then will the team know if they stand a chance on the real observation run. When they attempt to record an image of a black hole. An image of a black hole will provide a new way to test Einstein's most extreme theoretical predictions.
Einstein's equations show us that if you spend an hour or two at the edge of a black hole and then come back to Earth, for instance, Earth might have aged 10,000 or 1,000,000 or 1,000,000,000 years. So when we are observing the event horizon of a black hole, we are observing what really can be characterized as a time machine.
Yet despite Einstein's equations, even he didn't think that black holes could exist, that nature could ever allow them to form.
That's a sensible objection that Einstein had. I mean, after all, it'd be very, very, very hard to do to crush all the mass of something to a point. Einstein naturally and reasonably assumed that matter just wouldn't allow itself to be compacted that much.
But evidence of a mechanism has been growing. Scientists now believe a black hole is the corpse of a giant star that's gone supernova. Deep inside the debris, the surviving core collapses to an infinitely small point. This is called the singularity. Its intense gravity warps space and time so severely that nothing can escape, forming the black hole's event horizon.
It's possible that black holes are ultimately a figment of the mathematical equations that Einstein gave us, but how better to begin to push this understanding than to look and see what's actually out there? And that's the promise of the Event Horizon Telescope.
The team hope to test these theories by taking a picture of the black hole at the center of our galaxy. But they have an even bigger target, a black hole in the center of a different galaxy called M87.
There are only a couple of targets in the universe currently where the Event Horizon Telescope can hope to resolve this silhouette of a black hole, to see the edge of the event horizon. M87 is one of them.
This image of M87 is the closest astronomers have come to seeing a black hole. But to see its edge, Shep must zoom in much further.
If we want to image the event horizon, we have to make an image of what's inside this little box here at the very central core of this galaxy. That's what we've been directing all of our efforts towards for over a decade, to find out what happens in this place that has been off limits to us since the beginning of astronomy.
If they succeed, computer simulations show they should see this. Light bent into a ring and the shadow of the black hole.
If we could see this ring, it would be the best evidence that we have for the existence of black holes.
There are now just 2 weeks to go until the team will attempt to observe the black holes. And they're still working the problems. In Europe, Dutch astronomer Remo Telanus is in charge of managing the logistics of this global project.
Hey, morning.
Morning.
How are you guys doing?
Good.
I like that. That is what you guys did. The monitor. It looks very good. Thank you. Oh yeah, there.
It's taken 2 months for the team to process the test run data, but the results are finally in.
I know. Oh, some nice results to show you.
The data shows the telescopes have successfully linked together.
Even though they're apart by thousands of miles, they actually observed this source exactly at the same time. We did have problems because the South Pole telescope, it has moved by about 20 meters because the whole ice sheet moves.
That's quite unusual. I think there's no other telescope which does that, actually.
I hope not. No, I certainly hope not. We're in trouble then if that happens. That doesn't mean that the job is quite done yet. There are a few technical issues we need to take care of, but the core system works.
It's good news for the team. But Heino Falke, one of the project's leading physicists, knows how difficult linking all 8 telescopes will be.
If you go to these extreme experiments, you have to be extremely precise and take everything into account. You need to know the position to a fraction of a millimeter precisely. If you look at Hawaii, this is a volcanic region. This actually shifts due to plate tectonics by 6 centimeters per year. But, if you go to the South Pole, there's ice and that flows, and this can move by meters, 10 meters sometimes within years. So this really is the Formula One race car of the telescopes moving positions. And of course, let's not forget, away from the Earth is the moon. And that actually, it's affecting the entire globe. So some of the telescopes actually will be pulled by the gravity of the moon into one direction. They move half a meter up and down every 6 hours. And so,
with such incredible precision needed, the team need everything to go to plan.
Any telescope you lose will already significantly compromise your result. It will still be interesting. It'll just not be an image. It'll be some data and some plots that you show. It will not be an image.
Some of the others are very nervous, I believe, that they absolutely want to get the picture this year, but I'm more relaxed. I find it exciting just to be at the point that we can try to do this.
Remo has come to the Max Planck Institute for Radio Astronomy in Bonn to check the team's preparations. Here, hardware specialist Alan Roy is facing a problem that could jeopardize the entire project.
Hey, Alan. Hi. Good to see you. Hey. How are you doing?
Had a good trip?
Yeah, I had a good trip. It was fine. Oh man, so here's, it's happening here, the thermal problems, yeah.
The machines that record the data are overheating.
The problem with the recorders we have at the moment is they're getting too hot inside and they're shutting down. If that happens in the run, then that would stop us in our tracks. The observations we're making depends on having the whole array present. So, das ist aus Alu-Blech.
The problem is high altitude. The thin air at the telescopes means the cooling system is less effective. So Alan needs to make metal plates to deflect more cool air over the electronics.
Now. Sieht gut aus. See? So let's see if it fits. It's always a moment of tension, even in simple things. And yes, perfect.
Across the hall, Helga Rothman is in charge of over 500 hard drive units that can store millions of gigabytes of data.
Disk modules, they really contain the essence of what we want to do. The specialty about these, they are helium-filled disks, able to operate at very high altitudes. In terms of operational costs, this is the main factor. So buying disks is expensive. For example, we cannot afford to back up any data. And if it gets lost or broken, we practically lose that data, which is quite catastrophic.
That's my nightmare, that we'll have like a whole pallet full of these and they drop the pallet. That is just gonna be horrible.
Ramo must send the drives to each telescope location. It's just one small part of this global logistical feat. It's now 8 p.m. and Ramo's running a teleconference with the rest of the team.
The next issue I think I want to tackle is the outstanding tickets that we still have before we get to the observations. It is still
Just 2 weeks away from the observations, the pressures and tensions of the project are mounting.
The schedule starts at 3 p.m. local time at 0100 UTC.
There's nothing we can do about it anymore. I mean, these were discussed and have been discussed, so the schedules are what they are.
Just assume that it's going to be okay.
All right,
Nothing
well,
we can do about it.
No, I realize that. Okay, that's it, guys. Thanks all. We'll be in touch.
Bye.
Okay, bye-bye.
Thanks, bye.
It's taking 10 years to pull all these telescopes into the array, to equip them. We're all motivated by the same thing. We want to see that black hole, and that is ultimately what drives us. Get a glass of wine and go to bed. Seriously, that is what I now want to do.
There's now just 1 day to go before the make-or-break observations to photograph a black hole.
So move it here.
Imagine we had it kind of open.
In Massachusetts, Shep and physicist Demetrius Soltis are setting up a central communications hub.
Yeah, trying to have space around, so something like that. What do you see?
Now you're talking. Now you're talking.
This will be mission control.
Communication is vital to the entire project. I mean, we're synchronizing things to a microsecond. We need to make sure that everything is set up. We need to make sure all the tests have been run.
The team need to link 8 world-leading, multi-million-dollar observatories simultaneously to capture that image.
They've got clear blue skies, so...
They have a 10-day window at the telescopes, but clouds at any one of them could obscure the signal from the black hole and ruin the data. So each day, Shep needs to make a call. If the night is go or no go.
Whether or not you energize the Event Horizon telescope on a given night, that's the biggest decision you can make. If you make the right one, then you've got great data. If you make a wrong decision, you've expended huge amounts of resources.
Each night of observation will not only cost thousands of pounds, but also eat up their limited hard drive space. Shep needs 5 nights of data to stand the best chance of making an image. Judging the weather conditions across the world will be critical.
Pico might go above in the next couple of days.
The ALMA looks good. If you make the wrong go, no-go decision, you may have jeopardized your ability to image a black hole. And that's what consumes us when we're in that room. Hey, Kazu.
The communication and weather reports are online. Now Shep needs to make sure the telescopes are ready.
We want to make sure that we understand where things stand by the end of today, right? Because if something is not technically ready, then we really do have a problem.
In Hawaii, the volcano Mauna Kea is home to 2 observatories in the network. The James Clerk Maxwell Telescope and the Sub-Millimeter Array. Ramo has arrived from Europe, but the equipment still isn't ready.
Hey, Jonathan.
Oh, hi, Remo.
How's it going?
Not too bad.
Not too bad.
Lead engineer Jonathan Weintraub is still fitting the new cooling kits to his set of data recorders.
Excellent.
It was installed on Thursday, and then we were like, oh, damn, it doesn't have a cooling kit.
Oh, yeah, just
So we're putting in the...
yeah, it's a proper just-in-time management, I guess.
I guess, yeah. This is kind of last minute. This is kind of preventative maintenance. We don't want to suffer a failure due to overheating in the middle of the run.
Yeah, now the light turned on.
Here we go.
Yeah.
And there's air blowing out of these fans. So
yep. Excellent.
Okay, slide him in.
Remo and Jonathan must install the recorders and check they are all working.
Okay, there we go. That's it.
4 discs are there. Yep, all of them show up. Right. The very act of powering down and then powering up is to some degree stressful. I mean, sometimes you power something down and it never works again. So, you're always relieved when something works.
Whilst things are back on track in Hawaii, high in the Atacama Desert of Chile, Alan Roy has arrived from Germany to lead the observations at Apex.
Atento guardia de control, Apex 2, Apex 18.
Here, Alan is responsible for the most critical part of the project, the timing.
Timing is absolutely important to this project, absolutely central. It's the heart piece of the whole experiment. You're putting in a lot of effort, a lot of money, a lot of time, and it's all hinging on getting that timing right.
The Event Horizon Telescope network is so large, the emission from the black hole will arrive at each telescope at a different point in time. What's more, the Earth rotates. As it spins, the position of the telescopes in space constantly changes. If the team can't record the time the signals arrive to within a millionth of a second, the telescopes will fail to combine as one. To sync the telescopes together, the team have spent $2 million on some of the most accurate atomic clocks in the world, called hydrogen masers.
And this is the hydrogen maser. This clock keeps time to about a second in 10 million years. Of course, we don't wait 10 million years to measure it.
Alan must keep this clock at a stable temperature so it can run precisely. But there's a problem. The chamber used to cool it is broken.
The bearings have seized and we've got no cooling. So that means the chamber overheats and the maser is then not very happy.
A faulty maser could be catastrophic. In the remote Atacama Desert, it's too far to call out an engineer. Alan has only one improvised option available.
The solution is to crack open the door of the chamber so that the excess heat from the maser can come out through the door. Makes me a little nervous, but the clock, we have to take on faith, yes, that it's running as it should.
For now, this resourceful solution has to keep the clock running correctly, or the whole experiment could be at risk.
My hat is off to the folks that can actually undertake these experiments and observations and make it work. It's real, it's tangible, and it's extreme and abstract at the same time.
There's always a risk with these kind of measurements. They're difficult things. It requires so much care and finesse to bring all these pieces together.
Remarkably, the weather is clear at all 8 telescopes. In Hawaii, Remo hears from Mission Control.
So, just got the news. It's a go. So, ready to go and start observing.
This is the crucial moment that over 10 years of hard work has been leading up to.
It's taken a long time to get to this point that we're going to give it a real shot to get an image of a black hole. And now finally the day is here.
Remo must ascend to over 4,000 meters. to the top of the volcano. He had two observatories, the James Clerk Maxwell Telescope and the Sub-Millimeter Array are part of the network. And Ramo is up against the clock.
Right. We have to start tuning the receiver. This mirror directs the radiation into the receiver that we're going to use. It's like tuning your radio. It's going. Looking good.
At the Sub-Millimeter Array, engineer Jonathan Weintraub is in charge of recording the data.
We have 50 minutes now to run the checks before we start recording. And high altitude doesn't help your brain function. You tend to make more mistakes at altitude.
But across the mountain, Ramo hits a glitch.
Oh. What the heck? We fell out of lock.
The receiver won't lock onto the frequency. Without a lock, the data from the telescope will be ruined.
Maybe our yig is unlocked.
Ramo has no option but to manually adjust the receiver settings.
Darn. Am I now reading glasses? I can't see their stupid dials anymore. Yeah, we stayed in lock. Excellent. All right.
The team is ready, just in time.
I think we're all set.
Good. Great. It has a nice signal. Attention, attention. Doors and roof will be opening. Doors and roofs will be opening. Call station 42. Call station 42. Oh, TST is open.
Ramo directs the dish onto the target. And Jonathan gets ready to record the data.
5, 4, 3, 2, 1. Are we going?
The Event Horizon Telescope is on the way.
After over 10 years of work, the teams at 8 different observatories are finally fixing their gaze on a black hole. The team observe the emission from black holes M87 and Sagittarius A star and record data late into the night. After a 14-hour shift, Ramo must leave to avoid altitude sickness.
It's getting close to our 14 hours on the mountain. You're getting tired, and I will go down to the day facility, which is a little bit lower. But I will be sitting and monitoring there for quite a few more hours. But at least there will be more oxygen there, so that will help. Thank you for the support, and good luck, guys. The rest of the night, we'll see you tomorrow. All right, cheers.
Over the first 2 days of the run, the 8 telescopes around the world record 2 full nights of data. But in these extreme locations, the physical as well as mental challenges are taking their toll on the team.
It's hard physical work each day, and you feel it constantly on your body. The pulse rate is constantly elevated at altitude. It's constant stress on the system.
We're tired. You know, you wind up just being up at all hours of the night. People at high altitude are not always thinking perfectly.
Where is it? Where is this?
Oh, so it's in front?
We had a problem with one of the telescopes. One of the bits of electronics that we rely on was giving us some crazy results.
We're at the maser right now.
Look at channel number 17.
And ultimately, we fixed it because we were in the room, we're working.
So far, the weather has been perfect across the globe. But on day 3, at the Large Millimeter Telescope in Mexico, the outlook is beginning to change.
It's a scary, scary webcam. You know, the LMT is just completely chaotic right now. I mean, you saw the webcam, they're socked in by fog, there's clouds rolling in. It looks very, very dicey up there.
So it's clearly building up.
I mean, I'm not going to candy coat it for you guys. The decision for tonight largely rests with you, whether we go or not. It's a fool's game, right? You can't predict the weather 10 hours from now, especially the top of an extinct volcano with a big telescope on it. We got real solid, good weather at 1, 2, 3, 4, 5, 6 of our sites. 6 out of 8. Those are tremendous, tremendous odds. 2 of the key sites, they're marginal. The telescope in Mexico, the LMT, and the telescope in Arizona have dicey weather. And so we're just going to wait.
Shep delays the go, no-go decision. It's too close to call.
You guys have to explain these LMT webcams to me. From one direction, it just looks like a vacation paradise. And then for these other views, it just looks like you're heading into a vortex maelstrom of hell. And I don't understand how 3 different views can be so different.
Shep has to decide. But now there's news from the Alma Observatory in Chile.
Hold on. I want to make sure I understand what you just said. You think there's a chance that the data from last night from Alma are corrupted?
There's a chance.
Their entire second night of data could be corrupt.
This is a whole new wrinkle for us. If you had extra time, could you run this problem down?
Running it down is probably not likely.
If the data are corrupt, the team might now only have 1 night out of the 5 they need. With the weather set to get worse, Shep has to take a risk.
I think we should make this a go, because we're not going to tear the system apart, so we have to assume that Alma's going to be fine. So I'm going to say that we're going to go.
Over the next 4 days, the team let the storm pass and observe for another 2 nights.
We are recording the data.
Their hard drives fill up with over 6 million gigabytes of precious data. More storage than 12,000 laptop computers. If the team can make an image, it could unravel one of the biggest mysteries in physics today. What lies at the very center of a black hole? Einstein's equations suggest it's an infinitely small and dense point, the so-called singularity.
A singularity is a physicist's way of saying we do not know what the heck is going on.
In reality, at the dense core of a black hole, Einstein's equations don't make sense.
If you take Einstein's mathematics seriously and apply it right to the center of a black hole, then you do have infinite density. But there's no meter in the world that when you measure something goes infinity. Nature is kind of grabbing us by the lapel and slapping us in the face and saying, you don't understand what you're doing if infinity is cropping up as the answer.
Right now, frankly, the interior of a black hole is the Wild West of physics theorists. But the good news is, if you have a theory that predicts something different from Einstein for what happens inside, there's a good chance it also predicts something different from what happens immediately outside. It's just so exciting to finally, hopefully, start getting some clues from the Event Horizon telescope.
A picture of a black hole will take theory into reality. It could be the best physical evidence scientists have to figure out the mysteries deep inside, and could pave the way to a so-called theory of everything. It's 7 days into the run. At Mission Control, the team must now decide on what could be the final night of observation.
This will be our 5th night, and this way we'll have OPEX and ALMA at one end of a very sensitive baseline with really good weather at the other end of the baseline.
The weather looks clear around the world.
All right, so we're a go for tonight. Everybody, let's make it count.
For the last time, light from around the black holes is being recorded. In Chile, Alan Roy and the team finish what's been a tiring 8 days.
This is coming up to the end of the last run. We've got maybe 3 minutes. I'm feeling weary, but content.
The team have recorded their target of 5 nights of data. But only when they combine all the data together will they know if they can see a black hole.
This is the interesting part. It's almost a game of bluff. You've now spent more than a week here at the telescopes, observed through the night, and we still don't know if anything will come out of this.
Back at Mission Control, Shep is reflecting on the team's extraordinary accomplishment.
I mean, this is the beginning of the end, right? I mean, this is not the end by any stretch of the imagination. Even though we have all these disks, they could get lost in the mail. There are no backups. It's very, very difficult to copy all this data. So, you know, we're just a little nervous about some of that. You know, we have a lot of work to do, but we've taken this first big step.
We humans love exploring things to the limits of what's possible. And the event horizon is the ultimate limit.
I look at the audacity and the bravery, frankly, of the people who came up with a way of actually taking this incredible challenge and turning it into something that they are measuring today. It's mind-boggling.
At the South Pole, after 5 months of winter darkness, flights resume once again. Now the team can ship the last remaining hard drives holding the precious black hole data back to Massachusetts and Germany, and complete the processing from all 8 telescopes.
This is where a lot of the action has been because all the drives that you see here came from all over the globe. All the EHT sites have sent their drives here. And this correlator has been crunching through all of these drives.
5 months since the observations, the team can finally see if the telescopes linked together.
This one's from Spain. This one's from Hawaii. This one's from Mexico. So you're really seeing kind of like a UN of the astronomy world here. We're basically taking the light that was recorded from these sites out of the deep freeze, reanimating it, and then combining it as though it was being combined for the first time.
But data expert Vincent Fish finds a problem with the timing.
This cannot be right. You're me.
I'm amazed that nobody flagged this at observed time.
Oh, sweet Jesus.
They have discovered one of the network's atomic clocks in Spain was faulty.
You're really getting just random noise here.
Yeah.
Okay. We're pushing really the recording and the technology and the resolution to its absolute limits, right? And when you push something to the limits like this, you start uncovering these problems. There is a fix to this. I think we can correct for it so that we don't face this problem again. Wow, look at this. This is the delay.
Whilst the team resolve the timing glitches. In Cambridge, scientists from Arizona, Europe, and Japan have come to test how to turn the new data into images.
The big challenge that we face in this technique of the Event Horizon Telescope is that we don't have all the pixels in the image, if you will. We have some of the pixels, so the art is trying to figure out what the entire image looks like without having, everything that we'd like to have.
The team will test different computer algorithms to see if they can create an accurate image. But they won't attempt it on the target black holes just yet.
First, we're putting on training wheels, right? We're taking baby steps. And we're trying to use the algorithms that we want to use for SAG-A-Star and M87, but on well-known sources that are much brighter.
These bright sources come from matter swirling into what's believed to be a feasting black hole. As the black hole accelerates the matter, it rips it apart and launches jets of radiation into space. These are quasars. They can kick out more energy than 1 billion stars, leaving a signature jet that's visible across the cosmos.
If we can get really good images on those sources, then we know we'll be ready to go to the next phase.
Imaging scientist Katie Bauman is leading one of the teams trying to make an image of the quasar.
It's really exciting. The first time we're actually trying to make an image with the data. So here is 3C120. It looks like...
The quasar is too far away to see the black hole itself. But the team know what the jet should look like from existing telescopes.
Data can assess, is this,
But 2 days into this workshop, the algorithms are not producing one consistent image.
I can make an image that looks like that, and that's ridiculous.
We get a lot of different kind of structures come out from the same data. That's not a vote of confidence in those images, I guess.
Physicist Mareki Honma is also not getting a clear image.
Here is a very bright spot, so we believe there is something, but the whole area, it just looks like noise.
If the team can't get the algorithms to work for the quasar, they won't be able to make an image of the black hole. The team worked for a week adjusting the computer code. Finally, the algorithms start to work. And the team can see the quasar jet in more detail than ever before.
I see this jet-like kind of structure shooting out.
It's incredible. Look at all the structure.
The team has produced images now after going through this whole pipeline that seem very robust. And so that's the key. You have to be so confident in your techniques and your data handling that you trust them. Because for SAG-A-Star, for M87, we have no idea what we're going to see.
After over 10 years of planning,
Yay!
over 30 million pounds, and the combined brain power of over 200 international scientists.
Attention, attention, doors and roof will be opening.
Atento guardia de control, apex dos.
Finally, the time comes to try and make an image of a black hole.
This has been a huge process, a very, very careful process. And the imaging team is now getting the first set of data they can use to make a photo of a black hole.
It's really exciting. We just got the data, and that's, you know, what we've been waiting for many years, so it's a pretty exciting time for us.
This is the moment when we finally get to see what a black hole might look like.
Each member of the team loads the data and starts running their algorithms.
Are we doing this? Okay, ready, set, go, going.
The algorithms are producing some tantalizing images.
This is very early stages. This is exploratory surgery. The patient is on the table. We've opened the patient up. We're looking inside. We're trying to find out what we see.
Each member of the team needs to zero in on one consistent image.
That is interesting. Whoa.
I'm getting something pretty similar, a little bit.
And with the data for the black hole M87, one image soon becomes clear.
I see a circle-y feature.
An image the likes of which astronomers have never seen before.
What I'm seeing on the screen here is pretty startling. This is a case where the signal is so clear that it kind of hits you on the head with a hammer. If this holds up, it's going to be the discovery of my lifetime, and I think of many other people's lifetime. And it's really sobering to see what a black hole looks like for the first time.
The image shows photons of light being bent into a ring by the power of gravity. In the center, a black hole with a mass of 6 billion suns is swallowing the light that strays too close. It is profound evidence that confirms the existence of black holes, first predicted by Einstein's theory of gravity.
This shows us that space-time is distorted in the way that Einstein felt it would be at the black hole boundary, at the most extreme environment in the universe. These photons are struggling to get away from this black hole. And the black hole is tethering them with its immense gravity. And every once in a while, some of them can just get away from the black hole and come to us. So we're seeing the very definition of this surface where light is lost forever.
In 2019, the Event Horizon Telescope team verified their data and released their results to the world. This is a groundbreaking scientific result. But with plans for more telescopes and even better data, a picture of Sagittarius A star could soon be next.
When Galileo first proved that you can take pictures of the sky with telescopes, that didn't end astronomy. It started it. And in the same way, the most important scientific legacy of the Event Horizon Telescope is going to be the fact that it creates an entirely new field of science.
If I know astronomers, when this thing is done, they're going to go, ooh, what else can we do with this?
I can certainly envision that 10, 30, 50 years from now, our description of black holes are going to be completely, radically different.
For Shep and the Event Horizon Telescope team, they hope this is just the beginning.
We're not done. We don't actually like things to be tied up with a bow and finished. This shows us how black holes eat and how they feed in the way that has been impossible up to now. This, most of all, signals a whole new direction in astronomy. And that's rare. That is really extraordinary.
Do black holes hold the answer to the creation of the universe? Horizon delves into life before the Big Bang at 11:30. Next, here on BBC4, it sculpts universes and warps space and time. Professor Jim Al-Khalili on gravity and me.
It makes my heart pound.
It's quite easy to see Rembrandt as the evil